C. This is also an integral that has some limits here. So we're looking at that one. Everyone got that one okay? Okay. It's kind of small on here. Maybe you can zoom in the control room a little bit again. Yeah? Zoom in a little. Thanks. That'd be awesome. So we've got the integral from -5 to -2 of dx over 3x minus 1. What are you thinking? What's the first step? Anybody got an idea? Yeah, Jeff? You had one? U sub? Okay, what are you going to let u be? Okay, I like it, right? So if we let u be 3x minus 1, let's see how this works out. Du, what will the derivative be then? 3, yep, 3 dx. Which is good because we have a dx in there. We don't have the 3, but we can adjust for that. So I like to do it here. I'll just divide by 3 and make it 1/3. So now the dx matches up, and I'll replace that with 1/3 du. Or you can do that when you substitute. What else should I do on this one before I do the substitution? Yeah, the limits, right? So we're going to change the limits. I always think it's easier to change the limits if you're doing the u sub because then you don't have to go back to the x values. So here we have an x is -5, right, is the bottom limit, and x is -2. So we want to find their corresponding u values. Alright, so when x is -5, how do I figure out u? Yeah. Substitute it into the u equation, right? So that'll be, what is it, -15 minus 1 is -16? Good. I don't think you want to zoom out. That was zoom out. Zoom in. I think he's going to, hopefully. Zoom in! Better, yes. A little bit more. Alright. I got really small. Keep going a little. Zoom in a little more. There you go. That'll be pretty good, probably. I think I'll be able to see that. Okay, thank you. X equals -2. What does that give for you? -7? There we go. Okay, so now we make the substitution. So my new limits, which one should go on the bottom? -16, right? Because that's where -5 was. So make sure you do that. So -16 to -7. So the top gets replaced with the dx is really 1/3 du. The 1/3 you could pull out and just call that du, right? Constants you can pull out, or you can leave them in, it doesn't matter, but it's 1/3 du. Too far. I don't know if I can fit the whole page in. Zoom back out a little. And then the bottom will just be replaced with what? There we go, that's probably fine. The u. Yep. Okay, how are we going to integrate du over u? What are we going to do? Right. It's like u to the -1, isn't it? What's the integral for u to the -1? Remember what it was? Natural log. That's the one. You got to know that one, right? X to the -1, u to the -1. That's the natural log. So it's 1/3 natural log of u. Is that right? Absolute value. And that's going to be important in this problem. So make sure you put on absolute values. So when you integrate x to the -1, it's the natural log of the absolute value of, in this case, u. And then we're going to evaluate it from -16 to -7. Okay, so now when we do that, got to plug in the -7 first, right? So it'll be the 1/3 natural log of the absolute value of -7. Minus 1/3 natural log of the absolute value of -16. And that's important because if we had left those off, there is no natural log of -7. That's undefined. So now it just becomes 1/3 natural log of 7 minus 1/3 natural log of 16. Right? And we probably want to leave it like this. This is what we call the exact form. So that's usually how we want to leave it. We don't want to get a decimal or put this into our calculator. We usually want the exact form. Sometimes with natural logs, there's a bit of simplifying I could do, right? What would be another form of this? What can you do with subtraction in natural logs? It becomes division, yeah. So you can actually factor out the 1/3. And then combine this into division, and it'll become 1/3 natural log of 7/16. So that would be another form of the answer. So there are multiple forms. Sometimes when you're checking your answer in the back of the book, I would accept this or this. Those are all the same. So they're different forms of the same answer. There's probably something else you could do. What's a 1/3 in front? What can you do with a number in front? You can make it an exponent. And what's a 1/3 exponent? Cube root. That's right. So another form of this would be natural log of the cube root of 7/16. So, I mean, there's multiple forms of the right answer here. And for me, there's not one that's better than the other. Sometimes combining into one expression is nice, but really all three of those would be correct. Okay, so keep that in mind. Yeah. But you do want to keep exact form. Don't go to decimal form here. So, okay, so questions on that one? Anything with that one, make sure you got those absolute values on. That became important in this one. All right, let's look at the next one here. The integral of x plus 2 over the square root of x squared plus 4x. Okay, thoughts on this one? Who's got an idea for this one? Probably some sort of substitution, yeah, because I don't have a formula just for something in this form, right? So if I'm thinking a substitution, remember you're thinking you want to let it be some sort of inner function. What would we let it be here? Yeah, probably the x squared plus 4x, right? Because it's inside a square root. So I would think probably that's a good option, because then I can check the du and see if it shows up as the other piece of the integral. What is the derivative of x squared plus 4x? Let me ask Taylor over here. What's du? What's the derivative of x squared plus 4x? Right, 2x plus 4, right? With a, not plus c, but a dx. Yeah, that one will have a dx on it. In the end, we may add a plus c. But that's 2x plus 4, and I do like to write it like that because the dx does apply to the whole thing, so it should be in that form. Now, does this match up to the top of our integral? We want it, if u matches this piece, I want it to match the other. Is that going to match up? Yeah, if we factor out a 2, right? So let's do that. So let's factor out the 2, and then it becomes x plus 2 dx, right? Then it will match up if we divide by 2. Now that will match up x plus 2 dx. So this is a good choice then. So the substitution should work. I can let u be the inner part of that square root. Du will be this piece on the top. And they don't have limits to worry about. So let's go ahead and make the substitution. So in the denominator, are you just going to have u? Yeah, square root of u, right? So for the square root's still there. The whole top part is now a du with the 1/2, right? 1/2 du is replacing all of x plus 2 dx. So I'll just put the 1/2 out front. Though if you put it inside, that's not wrong. So, okay. Now how are we going to integrate when it's the square root of u in the denominator? Is that another case where it becomes the natural log of u? No. Okay. Because, let's remind ourselves, Natalie, what's the power if you have u, the square root of u? What's its power, really? You know what that is? 1/2. And if you bring it up to the numerator, then it becomes u to the negative 1/2. Exactly. So how I can write that, this is u to the 1/2, and I bring it up, it's u to the negative 1/2. So it's not really u to the negative 1, which is where we would get the natural log of u. This, we just now apply a power rule. So remember, any other power besides negative 1, we can just use the power rule here. So let's see, hopefully I got the name right. Joel, what would the new power be? U to the, yep. And what else would we have to do? Yep, because you're going to divide by 1/2 or multiply by 2, right? So don't forget, you're going to add 1 to the power, and then you're going to have to divide by the 1/2, which is the same as timesing by 2. You can write it either way, but both ways, those are going to cancel out. So that will be u to the 1/2. What else do we need with this one? Plus c. So is it just u to the 1/2 plus c? That's my final answer? It's good you're saying no. Why? Because... yeah, because you got to go back to x. That's exactly right. So u to the 1/2 plus c, you've got to go back and put it in terms of x. So we didn't have to in the other ones because we had some limits and we just plugged them in. But this one we'll have to go back and make our final answer in terms of x. So we'll plug that in. That becomes x squared plus 4x to the 1/2 plus c. Or how else could you write that? Yeah, that's exactly right. Or the square root of x squared plus 4x plus c. So either of those forms is fine. That was a 2 there. Sorry, I originally wrote a 4. I'll rewrite it underneath here. Yeah, so again, multiple forms, any of those forms is fine. Okay. All right, good. So here's a case where we have two terms. We get the derivative. If we factor out the 2, then it becomes something that we can use substitution. That will match up pretty well. So power rule on that one. Questions on that one at all? Okay. Okay, let's try this one. This is 1/2 t square root of t minus 4 dt. Okay, what are we thinking on this one? Are we thinking like a substitution here? What do you guys think? Maybe. Okay. If we do, what would we let u be? T minus 4. Okay. So if u is t minus 4, what is du? Derivative of t minus 4 is 1, right? So 1 dt. Is that right? You could just write dt. Okay, now does that match up to what we have in the rest of the integral? The dt does, but what else is in there? The t, right? So it's like I could replace this with du and that with u, but I have this like t there. Is this going to work very well? Maybe not so much. Let's see. Could we adjust for that? Okay, you could find out what t is. What is t? You said it was u plus 4? Okay. Is that okay? Can we then replace a t with a u plus 4? Well, let's try it and see. Okay, so we had this extra leftover t and it didn't really match up into the du. However, I could get an expression for t by solving this for t, which is u plus 4. So let's see if we make the substitution for all the pieces, if it's something we can integrate. So that's really the question is, if I do the substitution, can I integrate this? So the t would be replaced with u plus 4, right? So I'm going to put that in. What is this piece going to look like? The square root of u, right? And what's dt going to be? du. Okay. So, does this seem like something I could integrate? Yeah, what do you think, Jeff? No? Not in this form, right? Is there a way I could simplify this and still integrate? What would you do, Benham? Okay, how do you get rid of parentheses? Usually you distribute, right? So what if we distribute it? Okay, so in this form, you can't integrate this. It's a product, which is kind of hard. You don't have any techniques for that yet. But if I could distribute and get rid of the parentheses, maybe it's possible. I'm going to pull the 1/2 out front. What happens when you take a u to the u square root of u times a u? U to the 3/2. You add the 1 plus this power is 1/2, so 3/2. And then you would have 4 square root of u, right? But that's just u to the 1/2. Now could I integrate it? Yes. Now that you've made terms, these I can just integrate using the power rule, right? So it didn't necessarily look like at first, but if I can distribute, then I can integrate this. Notice, is that something I could have done at the beginning? Could I have distributed the t over a square root? Not usually. Not usually over square root, over parentheses, yes. But in a square root, no. So a substitution is necessary here. It's kind of a different substitution where you not only substitute this, but the t as well. And then we can distribute because we no longer have two terms under a square root. So we only have the one, and that's easy to distribute. So let's see if we can finish this one off. So keep that in mind. You usually can't distribute into like a square root like that, or if it has a power on it, addition or subtraction with a power. But if it's by itself, you can distribute into over parentheses like that. Okay, so let's see. Angie, help me out with this one. I think we're up to you. What's the new power on u going to be for u to the 3/2? You know what that will be if you use the power rule? Okay, that's right. Benjamin Helper, what does u to the 3 halves become?
It's going to be u to 3 half plus 1, which
Right.
is u to 5 over 2 multiplied by 2 over 5.
Yep. So remember, you just add 1 to the power. So 1 plus 3 halves is 5 halves. Then you got to divide by 5 halves, which is the same as multiplying by 2 fifths. So you should have 2 fifths u to the 5 halves, however you want to write that. McKelty, what about the 4u to the 1 half? What will that become?
It'll be u to 3 halves.
Yeah.
And then multiplied by 2 thirds.
Good. And I'll just write on this side since I ran a room on the left. So that's right. So add 1 to that as well as 3 halves. Divide by 3 halves is multiplying by 2 thirds. Okay, so let's simplify a bit here. So this one's just 2 fifths u to the 5 halves. If I multiply 4 by 2 thirds, I get 8 thirds u to the 3 halves. Of course, I need a plus c. I'll keep putting those on. And what else do I need to do here, Jessica? Can I leave it like in this form? What would you do to finish this off? Okay. So she's going to multiply the half in, which is fine because it will simplify a little bit. The 2's cancel and you get 1 fifth. U to the 5 halves. This one, that reduces to 4 thirds. U to the 3 halves. Plus C. Anything else? Yeah, Jonathan's saying you got to put it back in terms of T, right? So don't forget, you don't usually want to leave it in terms of U. Ever, really, if you're doing a u substitution. You want to go back to the original variable, or if it has limits, you'll plug in the limits, but you don't ever want to leave a u. So that's right. So we'll plug this back in. What was our u again? It was t minus 4. So t minus 4 to the 5 halves. 1 fifth t minus 4 to the 5 halves plus 4 thirds t minus 4 to the 3 halves. And your plus c. And the 5 halves and 3 halves, you can rewrite those as roots and things like that, but so that would be an acceptable way to do it as well, but I'm just going to leave it like that. Okay, so that one was a little bit different, but you can do that. You can make an adjustment on u and solve it for t and then substitute that in. The main thing with substitution is you want to be able to put everything in terms of u. Can I do that? If it's possible, yes. And once you do, is it something you can integrate? So hopefully it makes a form that you can integrate, or by simplifying gives you a form that you can integrate. Otherwise, why do the u substitution if it doesn't really get you anywhere that will allow you to integrate? So that's one thing that's important about substitution. Questions on that one? Okay. All right. Let's go to this one. Next is the integral of tangent squared of 2x. That's an interesting one, right? Do we have a formula for tangent squared, the integral of that? Remember, we had them listed on the front page. Do you remember? Anything for tangent squared? I don't remember one for tangent squared. Do you? No. What do we have for squared? So we have secant squared. There's a formula for it, right? And cosecant squared. So, here's the question then. So if I can't integrate tangent squared, could I replace tangent squared with one of those other two that I do know how to integrate? So is there a relationship between tangent squared and secant squared? Or cosecant squared? There is secant squared, right? And remember, this is one of those Pythagorean identities. Here's where your trig comes in. What is tangent squared equal to? Or do you remember the relationship? What's the formula? 1 plus tangent squared equals secant squared. Yes, this is the formula. 1 plus the tangent squared equals the secant squared. Does that sound familiar? Vaguely. A long time ago? Okay. It is a true statement. 1 plus the tangent squared equals the secant squared. So, if I wanted to make the replacement for tangent squared, what would it be equal to? Yeah, secant squared of x minus 1, right? So we're going to use that identity here. Because I can't integrate tangent squared, I've got to put it into terms of something I can. So let's do that. So this becomes then the secant squared. Can I just make a replacement for 2x, right? It's still 2x minus 1 dx. so I'm just going to use that identity. And there's a 2x, so obviously I keep that. Okay, now can I integrate this? Well, do I have a formula for secant squared? Yeah. Do I have a formula for integrating 1? Sure. Okay, the only problem is it's secant squared of x, right? How am I going to adjust for 2x? Yeah, substitution. So you can split these up into 2 integrals, right, and do them separately. So I'm going to integrate the secant squared of 2x and the 1 of 2x. This one, though, will probably require a short substitution, right, because it's not just x that I have in there. So I'll have to make that u a 2x, and so adjust for that. The derivative of 2x would be 2, right, dx. And so I'll have to adjust by a 1/2 here. Okay, so when I do the substitution, I'll have the secant squared of u now. And then the dx is replaced by the 1/2 and the du. Okay. So again, that becomes u. I have the 1/2 du. What is the integral of secant squared? Remembers, what was it? Tangent. Tangent, yep. It's the tangent. So the integral of secant squared just becomes the tangent. We have 1/2 tangent u plus c. What is the integral of 1? Let's see, is it Taft? Is that right? Taft? What's the integral of 1? Yeah, so this one just becomes x, right? So can I just add 1/2 tan u and the x and then the c? Oh, wait a minute. Something seems off, right? What do I got to do? Yeah, so don't forget you don't want to leave u again. So as long as I put him back in terms of x, we should be fine. So that's a 2x. Then I can go ahead and add the x in from that. And I only really need to put on 1 plus c. Technically, they each have 1. But adding the two constants together just make another constant. So you can just make 1 plus c at the end. So was it minus? Oh, thank you very much. It was a minus. Thank you for pointing that out from here. All right, very good. Okay, so there's one where the trig starts to come in. So this one, we did do a substitution, but really just for the 2x. So in order to integrate tangent squared, there's no real formula for that. So then you got to think of, okay, trig identities, there's some way I could change that. So it is possible then for me to actually be able to integrate that. And that's a good formula to know. 1 plus tangent squared equals secant squared. What are some other identities? Sine squared plus cosine squared equals 1. What else do we know? 1 plus the cotangent squared equals the cosecant squared. Yeah. So don't forget those Pythagorean identities. They show up every once in a while. Okay. Let's look at G here. The integral of 7e to the cosine of x times sine of x dx. Okay, let's think about how to start this one. What do you guys think? What are you thinking? Ideas? U sub? So you're thinking U substitution? You thinking cosine? I like that idea because what's its derivative? The sine. So I think that'll work well because then I can get rid of this. This will all be part of the du, right? So is the derivative just sine? Actually, what is it? Negative sine, yeah. So negative sine of x dx. So we'll just have to adjust the negative here, but otherwise it will match up to what's left in my integral. So when I substitute, what will the new integral look like? Riley, why don't you help us out with that? What will it look like if I put in all the u and du's? So what would it be? You'd have a 7, right? And then what? Yep, and you can put that in front. Good. We'd still have e, right? But it would be e to the what? What's cosine now? Yeah, so that will be our u, right? Cosine will be the u. And all of this will be taken care of by du. And then you'll need the negative as well, but I'll just put it out front. So yes, that becomes u. This all is part of du. which is nice. And then, of course, you'll need the negative, but we'll put that out front. Do we know how to integrate e to the u? We should, yes. And in fact, yeah, it's just e to the u, Jessica said. That's exactly right, e to the u. Easiest one to remember. So this is just negative 7 e to the u plus c, right? Good? You're circling this and turning that in? No, Jeff, what are we doing? Yeah, plug the x back in. Very good. So that would be negative 7 e to the cosine of x plus c. Yeah, so just plug your u back in so it's going back in terms of x. Then you can be done. Yeah, so that one makes it nice when I put in the u. It's just e to the u, then du, and that's pretty easy to integrate. So very good. Okay, now let's go to another trig one. That one was trig, but we didn't really do any sort of trig identities. We just used the relationship between the trig and its derivative. So let's see what's going on in h here. We have the integral of cosecant squared over 1 plus cotangent x. Okay, what are we going to do with this? Obviously, you can't integrate it just like this. What could we do? Is there some relationship between cotangent and the cosecant squared? Yes. What is the relationship? Is it... Yeah, one is the derivative of the other, right? What is the derivative? Which one's the derivative? Which one should be u? Which one is the derivative? Cosecant squared is the what? Is the derivative, isn't it? Of what? Cotangent, right? So that's what we want to let be u. So I probably want u to be, should I make it the cotangent x or cotangent x plus 1? Or does it matter?
Cotangent x plus 1.
Okay, we'll try that, right? Maybe it doesn't matter. If you do the whole thing, what's its derivative? Du. Right, and it's actually, there's also what with it? Negative cosecant squared x, right? Dx. So it actually is negative cosecant squared dx. So would it have mattered if I'd taken off the 1? Probably not. You would still get the same derivative, right? So it will still match up to the numerator. So here it actually probably wouldn't necessarily matter. Down here you would either have a u or a u plus 1. So on this one, maybe it wouldn't make a difference as long as we had the derivative the same as what's in the numerator there. So we'll adjust for the negative here to the other side. And then we'll go ahead and substitute. Okay, so what are we going to get when we substitute? What will it look like? Let's see. Salvador, want to help us? What will it look like? Where will the u and du be? Any idea? And if you don't know, that's fine to pass, but what do you think? Would you say negative on top? Okay. And then what else? And all of this is a du, right? So negative du. And what will be the bottom? Yeah, the u, right? All of that makes up the u. So it looks like I'm going to have negative du, that replaces the top, and 1 plus cotangent x is our u. Is this something I could integrate?
Yes.
Yeah, we should be able to, right? Let's switch the form. Pull out the negative, and what if you called it u to the negative 1? You could probably recognize what to do, I hope. Jonathan P. here on campus, what do you think you do now? What do you get for u to the negative 1? What's its integral? Do you remember? You gotta remember those. It's hard. It's like x to the negative 1. Nathan, you want to help him out? Do you know? What is it? That's the natural log. Yep. Does that ring a bell now? The natural log. So when you have x to the negative 1 or u to the negative 1 or anything with the negative 1 power, that's going to always integrate to the natural log of the absolute value of u. And the negative will just stay out front there. So negative ln of natural log of u plus c. And then, Kobe, what's my final answer going to be? Good. So what do I got to write it as? Yep. And then the plus c. Very good. So good. So again, don't leave it in terms of u. Make sure you plug in u back in. So that's the cotangent of x plus 1. Good. And you'll notice if you had done the 1 plus u, maybe just let u be cotangent, you would have 1 plus u down here, and your natural log would be 1 plus u, and so you would still end up with the same answer. So on this one, actually probably wouldn't matter if you had let u be cotangent x or cotangent x plus 1. In the end, you get the same answer for those. So, all right, so here we kind of had to think about the relationship. Is there one between cotangent and cosecant squared? And there is. One of them is the derivative of the other. So then it's usually a good option to use substitution there. One part can be u and one part can be du. Okay, so let's see. One more for us to do. This one has some limits, 0 to 1. We have the 4th root of w plus 1 squared dw. Okay, so let's think about how to integrate this one. Usually can't integrate this one just as it is because we have terms inside the squared here. Any thoughts on this one? Square it? Is that what you said? I like it. It's not hard to square something, right? How do you square something? Foil it out, yeah, like distribute out times itself, right? So if we took the 4th root of w plus 1 and times it by itself, that's not too hard to do. So this means to multiply times itself. What's the 4th root of w? It's like w to the 1/4, right? So if we FOIL that out, what do we get? W to the 1/4 times w to the 1/4 is w to the 1/2. Good. Add 1/4 and 1/4 is 2/4. On the outside, you'll have 1 w to the 1/4 and another one. So if you add the middle two terms together, you get 2 w to the 1/4. And then 1 times 1 is 1. So we just added the middle terms together. Does this seem like something I could integrate once I've FOILed it out? What do you think now? In this form? Sure, because they're all separate terms and they all have powers. I can just use a power rule. So I'm just going to FOIL that out. I get w to the 1/2, 2w to the 1/4 plus 1 dw. And once I FOIL it out, that shouldn't be too hard to integrate. So this one didn't really require a substitution. Just a bit of simplifying, and then you can get to the answer here. So let's see. Brandy in the back, help me out with this one. What would you get for w to the 1/2 if you applied the power rule? You know what that would be? Not sure? Okay, what about David? Do you know what did you say? Oh, what would you get if you integrate w to the 1/2? Very good. Yep. So remember, you add 1. So you add 1 to the power and you get 3/2, and then you divide by that, which is the same as multiplying by 2/3. Excellent. Let's see, Jim, what do you think we would get for 2w to the 1/4 if you did a power rule? If you add 1. Good. Yep. And I think then you'd have to multiply it by 4/5. So you would have 8 over, you were right about the 8 over 5. Does that make sense? So you took basically the 2 times the 4/5. So that becomes an 8/5. And you can do that in 2 separate steps if you want. But yeah, so 2 times the 4/5. So that's an 8/5. Okay. And Michael, what do we get for the 1? What are we going to get when we integrate that? You'll get something. Yeah, except this one's not x, it's w. There you go. Yeah, be careful. I was trying to put on the x too, but it's actually w here. And then the only other thing we need is a plus c. So I think that's it. Oh, limits. Thank you very much. Not a plus c. How about 0 and 1? That'll help us out. Okay, let's do it. Limits of 0 and 1. Well, those seem pretty easy to plug in, actually. Because if you plug in 1, all you're going to get is what? 2/3 plus 8/5 plus 1? What are you going to get when you plug in 0? Zeros. 0, 0, 0. So that's all 0. So I don't need to worry about that. So I really just need to add in the 2/3, the 8/5, and the 1 and see what you're going to get there. So make them all 15ths and add them together. All right, I'll do it by hand. You do it on your calculator if you want. So let's see, that's 10, 24, 34, 25, 49, 20, 49 15ths? I think so. 49 15ths? You want to check me? Okay, good. All right. So 49/15. Thanks for reminding me about the limits. Awesome. Okay, so lots of different integration techniques. We use substitution a lot, but something like this, sometimes you just got to simplify or maybe use a trig identity, but the goal is to get it into a form that you know how to integrate. So using some formula that we know from the beginning that we talked about. Any questions on any of those you want to ask about? Anything right now? Okay, I'm going to give you two new integrals that you can know here that you probably haven't seen so far. We actually have an integral for all the trig functions except these last two, so I'm going to give you formulas for those. So we know what the integral of sine is, we know what the integral of cosine is, we have it for tangent, we have it for cotangent. The only two we haven't seen so far, if you took Calc 1 here anyway, is secant and the cosecant. So I'm going to show you how to do it. I'll show you the derivation so you kind of know how we get there. You don't necessarily need to memorize the derivation, you can just memorize the result, but it's kind of interesting to know. So secant by itself would be hard to integrate. It's 1 over cosine, so cosine is there in the denominator. So by itself is difficult to integrate. So we use a technique to integrate this called multiplying by a fraction that really is a form of 1. So we're going to make a clever choice though. So we're going to use here a secant x plus a tangent x. And we're going to make that into a fraction that would reduce down to 1, so we're not really changing the integral here. So we're going to take what it is, and we're going to multiply the numerator and denominator by secant x plus tangent x. You're like, how did I randomly pick that? Well, it wasn't random, but it will turn out to help us a lot be able to integrate this. But notice I'm not really changing, I'm just multiplying by a form of 1. So let's go ahead and multiply through the numerator. Remember, this is over 1, so this applies to the numerator. So this becomes secant squared x plus a secant x tangent x. The bottom is still just secant x plus tangent x. And now, maybe you can think about why this was an important choice. Yeah, there is some relationship. Do you see the relationships we have?
The derivative is there.
The derivative's there. What's the derivative of tangent? Secant squared. What's the derivative of secant? Secant tangent, yeah. So you see these trig functions on the bottom have their derivatives up here. So multiplying by that gave us something nice that we can do a substitution then for. So if we let u be the denominator, the derivatives will show up in the numerator and be our du. So then it becomes quite easy to integrate this. So if we take this as our u, the derivative of secant is secant x tangent x, and the derivative of tangent is secant squared. And so when I substitute then, the whole numerator is exactly this, secant squared plus secant tangent, in a different order, but that doesn't matter. So that's all du, and the denominator is our u. Okay, so let me go to Kimberly. Let's see, Ethan and Kimberly, what's the integral of du over u? Do you remember what that becomes? That's right, because it's u to the negative 1. So it's the ln of the absolute value of u plus c. You got it. And then we can go ahead and plug our u back in. So it becomes the natural log of the absolute value of secant x plus tangent x plus c. Okay. So that's how you integrate the secant. Alright, and of course secant x plus tangent, those can switch order, but that's the general rule. So I'll write it down, the result down here. So now you know the integral of secant is this natural log right here. And secant can go first or tangent, it doesn't matter inside there, but that will be one more rule that you can use. So you don't need to show the derivation if you want. If you ever have to integrate secant, you can use the result now here. Okay, so now we know how to integrate secant. The last one is cosecant, and you can do something kind of similar. You can multiply by a fraction here. That also kind of comes up with a clever result. So here what we're going to use is cosecant x minus cotangent x in the numerator and denominator. So cosecant x minus cotangent x. And we're going to do something very similar. We'll distribute the numerator through, and then hopefully be able to use a u substitution. So we'll get cosecant squared x minus cosecant x cotangent x all over cosecant x minus cotangent x. And can you see some relationships again, hopefully? What's the derivative of cosecant? You know what that is? Cosecant cotangent. And what's the derivative of cotangent? Cosecant squared. Technically negative, but a negative cotangent would make it a positive cosecant squared. So yeah, we can do the same exact thing. So if we let this be our u, cosecant x minus cotangent x, then du is negative, the derivative of this is negative cosecant cotangent x, and the derivative of cotangent is negative cosecant squared, so that will make it positive there. And it will match up exactly to the numerator again. Don't even need to adjust signs. So that's why we chose cosecant minus cotangent. So this one will work the same way. You'll get du over u. And everyone knows what this integrates to now, right? du over u. The natural log of the absolute value of u. So this time we'll get the natural log of the absolute value, put the u back in, cosecant x minus cotangent x plus c. So that's your final rule that you know now, is how to integrate cosecant. That's the result, the natural log of cosecant x minus cotangent x plus c. Okay, so that's one more. You can add to that the list of formulas at the top there to know. So, okay, kind of interesting how they integrate those, but that's the technique they use. So we can actually integrate all 6 trig functions now. So there's a formula. Jonathan and Haley, yeah. But, well, in the front, what happens is if you let u be this, cosecant minus cotangent, the derivative of cosecant is negative cosecant cotangent, does have the opposite sign. The derivative of cotangent is technically negative cosecant squared, but the negative in front of that and the negative in front of the cosecant squared will make it positive. So then they will match up exactly to the right signs. So they actually do match up and get you the right signs there. Okay. All right. Well, the last thing I'm going to show you is Graphmatica. So let's look at a couple things on Graphmatica here before we leave. Do you have that at the end there? Okay, good. Graphmatica you can download for free. At www.graphmatica.com is what it's called. If you know of another graphing application, you're welcome to use it. I'm not saying you have to use Graphmatica, but this is the one that's free that I know about, know how to use pretty well. And it is installed on some of the computers around campus, so it's pretty easy to use. But this is what it looks like when you open it up. It's very easy to graph things. You just kind of need to know a little bit of the formatting and notation. So just going back to this problem, this one asks us to find the integral of this and graph that and its antiderivative using c as 0 to check the answer is reasonable. So let's go ahead and integrate this a minute. So 2 cosine of 2x plus 2x, let's find its integral. Can we integrate this? 2 cosine of 2x, do we know how to integrate cosine? Sure. You might have to do a u sub, right, for the 2x. Sometimes I kind of skip when it's u equals 2x. If u equals 2x, what are you going to have to adjust by? What's the du going to be? You're going to have an extra what for the derivative? 2. So you're going to have to adjust by a half. So I just know that... Oh, I thought someone was telling us something. So here, you can do a u sub, but sometimes I'll just do that part in my head. I'm like, if u is 2x, all I'm going to have to adjust by is a 2, so I'm going to have to pull out a half, right? So if I do that, I pull out a half, and then the integral of cosine is sine, right? So this is just 1/2 2 sine of 2x. So if you don't want to do the u sub, you can. But the derivative of the inside is just a constant. That's all you have to work with. Then it's usually, you can do that without a u sub. What's the integral of 2x? You know what that's going to be? Yeah, so that becomes 2x squared over 2, right? You add 1 to the power. 1 plus 1 is 2, divide by 2. So those cancel, and you just get x squared plus c. So just simplifying this a bit, these also cancel. So you'll just have sine of 2x plus x squared plus c. That's its integral. So the two things you're going to want to graph are the original function, which was 2 cosine of 2x plus 2x, and then its antiderivative, its integral, which was sine of 2x plus x squared, and they say here to use c as 0, so you can leave that part off. Now, I realize we're out of time, so actually I better stop, so I don't want to keep anyone. I know sometimes you guys have classes to go to, and so do I. So here's a